So we keep saying light is important for photosynthesis, and there is a euphoric zone down to which there is enough light for photosynthesis. So what exactly happens? So we will look at the spectrum of light. You probably already know that the solar radiation, the energy that is emitted from the sun, is an electromagnetic spectrum that goes all the way from very high gamma rays, X-rays, and so on into very strong UV that gets used up in the stratosphere for producing ozone. Some of the UV gets absorbed by the ozone, and there is a lot of infrared energy that we cannot see. And majority of the energy that reaches us is in the visible. Blue wavelengths penetrate the deepest in the ocean. They are scattered most by the water and also by the air. That's why the ocean tends to look blue, or a big body of lake can also look blue, and the sky looks blue, right? Longer wavelengths have lower energy, so we will see that they're absorbed at the very top of the ocean waters. So you can see here we are going from cosmic rays, gamma rays, and X-rays down to UV, and most of the energy that actually makes it through the atmosphere is in the visible. All those colors: violet, blue, green, yellow, orange, and red. And then you have the infrared. We emit infrared that we cannot see, but many animals can see, and you can find infrared goggles. Why? Because they want to see who's running around at night doing things that they shouldn't be doing, right? Then it goes on to longer wavelengths all the way to microwaves, radio waves, and so on. So the spectrum of visible that's hitting the ocean, you can see here the depth, 1 meter, 10 meters down to 100 meters. So blue has higher energy on this end, and violet, they are making it down to deeper depths, and green, yellow are also making it down, but they're only down to 1% by the time they reach 100 meters. And the red and orange are mostly disappearing by the time they reach about 1 meter. Okay, that's the transmission of light into the ocean water. This is something that's important. How do we measure the depths of light? The oldest method was invented a long time ago by a guy called Secchi, the Secchi disc, which is just basically a disc which is painted white, and it's tied to a rope, and you lower it on the side of the boat or the ship or pier that you are sitting on, and you keep seeing the length of the rope that is taken before the disk disappears. It doesn't say the amount of light, but it just says visibility down to that depth till you can see the disk, right? That's the Secchi disk, and they have recorded Secchi disk penetration depths of light for a long time. People have used it for various purposes. Obviously, turbidity from rivers and photosynthetic pigments themselves will block light penetrating deeper into the water. Color in the ocean is related to photosynthesis, right? I think you already know the concept. Color is what is reflected. So if I'm wearing a blue shirt, that means it's not absorbing blue, it's absorbing everything else, and so on, right? So if you see light green algae, that means they are absorbing everything except green, right? So coastal and upwelling areas are productive, as we already said, tend to be light green in color. They are eutrophic. This is a new term for you, maybe. U is always good, right? Of course, it's euthanasia, then it's complicated, but eutrophic means there is enough nutrients, sometimes too many nutrients. And the open ocean, we will again look at the ocean color more carefully. We had said this before already, that where the Hadley cell comes down, there is subsidence, high pressure, clear skies, and no rain. That's where the land deserts tend to be. But that's also where the ocean deserts are, because there are very few nutrients at the surface. There are complications because light penetrates and there are nutrients below the surface, so you can have subsurface chlorophyll and primary production, which cannot easily be measured by the satellite, because satellite only sees about 10 to 100 meters depending on how clear the water is and so on. Anyways, coastal waters are clearly eutrophic, highly productive, rich in nutrients, whereas the open ocean tends to lack nutrients, even though there may be a lot of light. Clear skies, high pressure means a lot of light, but no nutrients. So they tend to look dark blue because blue penetrates deep and water molecules scatter it in every direction, so our eye preferentially receives the scattered blue light. Okay, so those are called oligotrophic waters. Oligotrophic waters. So here is the ocean color again, and you can see large areas of blue. Now you go to your physics and say, I know that is right under the high pressure of the subtropical gyres, and there are also subpolar gyres, but you can see that only appears seasonally. So in some season, which is obviously the winter season, when there is no light, no productivity, so in the winter season, high latitudes and subpolar gyres tend to have blue colors. Blue means desert, ocean, desert, ocean, desert. Okay, Hadley cell comes down, convergence happens, nutrients are pushed down, upwelling, nutrients up, downwelling, convergence means nutrients down. Okay, so the oligotrophic gyres are blue, and these colors are where there is production. Of course, there are rivers like the Congo Zaire River here, Ganga, Brahmaputra, Irrawaddy River here, and so on and so forth. But you can recognize your strong upwelling regions where there is good green, red, yellow colors, high productivity. At high latitudes, the productivity occurs in the season when light becomes available. We will look at the seasonal variability of the production a little bit later on in more detail. There's another little trivia here. Of course, you can also see that wherever there are islands, primary production tends to be high, because as we said before, as the currents flow, it can force up the water and create island upwelling. So islands tend to be productive at least on one side, depending on which way the currents are flowing. Okay. The other thing is, if you look at the ocean color here in the Atlantic and in the Pacific Ocean, the equator is very clearly marked. Why? Because that's where Ekman divergence and upwelling happens. That's where maximum primary production in the open ocean happens. Open ocean is mostly lacking nutrients and oligotrophic, but upwelling regions are not. So open ocean upwelling is productive. But if you look at humidity, winds, clouds, rain, and so on, remember your ITCZ and so on, which is not on the equator. So ITCZ is in fact called the meteorological equator, where the winds converge and the air rises and rainfall happens. So it's only the ocean color that can show you the geographical equator from space, because that captures the upwelling and the production on the equator. If you look at any other meteorological product from satellites, they will mostly not show the equator very clearly at all, whereas the ocean color clearly shows the equator. This is just showing the seasonal migration of the sun and the production even on land. But if you look at interannual variability, year to year chlorophyll, obviously we'll also see El Nino and so on, because during El Nino, waters in the east are warm, upwelling is reduced, chlorophyll will be reduced, and so on, right? So just think about it. You have to combine your physics with the biology and the circulation, nutrient availability, etc., etc. We'll also look more carefully at the Southern Ocean, which is a very interesting channel ocean, which has very high productivity and so on. So biology is always the most interesting part of learning, right? Especially when you can combine physics, chemistry, and biology, which is done very well in the ocean. Oceanography is exciting once you add biology and chemistry to it. Okay, most important and exciting physical concept was the western boundary intensification about vorticity and mass balance that you learned, and then you add biology, you get amazing things to learn. Fun!